Hello, everyone. I'm Xia from MIT CCL. Today, I'm going to talk about Taurus, a lightweight parallel logging scheme for memory databases. So this work is jointly done by Xiangyao from University of Wisconsin-Madison and Pavlo from Carnegie Mellon and Srinivas, my advisor from MIT CCL. So the motivation is that conventional serial logging scheme has become a major scalability bottleneck in modern databases. But in contrast, parallel logging can better suit the demand of modern in-memory databases. So Taurus achieves parallel logging and recovery for both data and command logging by tracking coarse-grained data dependency from using vector clocks. So the transactions come at different times and they form very complicated dependencies among each other. Especially a single transaction might depend on a number of other transactions. We figure out that it is actually not necessary to detailed record all these dependencies because recovery, we might not need this many parallelism during recovery. So instead, we choose to log very coarse-grained dependency information. Basically, instead of log one-to-one dependency information, we record the dependency from a single transaction to a group of transactions. But the question is, which group? So here in this work, we use the log sequence number vectors as a coarse-grained description of dependencies. So the idea is very similar to the vector clock, the land-port vector clock. So basically, let's say if these log record actually depends on these 4 transactions colored in green. So instead of taking instead of recording the number of these 4 transactions, we just record a single log sequence number per log, and we just use the maximum of the log record number of those transactions that this record depends on. So for example, here, for the first log, we just record a single number 16. And for the second log, we record 2. And for the third log, we just record 7. So this vector has the same size of the number of logs. We just know that so this transaction will not depend on any transactions after this log sequence number. So the third intuition is that we want to propagate dependency using tuple metadata. So we not only assign LSN vectors to transactions, but we also assign LSN vectors to tuples. So for example, here, the first transaction 1, has initially the LSN vector to be 0, 0. And it visits a tuple with LV to be 4, 2. Then it will just update it to LV to be 4, 2. Then maybe after a while, it visits other tuples, and finally it will log itself to the buffer, and then update. Let's say right now the LV of this transaction is 7, 9. Then it will update the tuple LV to be 7, 9. Then later, for example, transaction 2 visit this tuple again and update the LV of itself to be 7, 9. So notice that by this whole process, transaction 2 actually forms a dependency on transaction 1 by updating this LV. So we use a lot of LSN vectors. First of all, we assign a LV for each transaction, and we assign 2 LVs, basically the read LV and the write LV for every tuple. The read LV of a tuple basically indicates the LV of the last transaction that has read this tuple. And similarly, the write LV basically indicates the LV of the latest transaction that has written this tuple. And also we maintain a global persisted vector. Basically, this keeps track of how much we have flashed each file to the disk. So whenever a transaction writes to a tuple, so after fetching the exclusive log, it will also update the LB of itself to be the element-wise max of the write LB and read LB of the tuple and itself. So similarly for read operation, after fetching the shared log, the transaction updates t.lv to be the element-wise max of tuple.write LB. This is to track the read after write dependency. So when the transaction is ready to commit, it will write a log record together with the LB of this transaction into the log buffer. So after writing, this will generate a new log sequence number. So the transaction will just update the corresponding dimension. So let's say the transaction belongs to the ith log. So it will update the ith dimension to be the new LSN. And also, it will update the LSN vectors of the tuples in the access set. So because this transaction access, it has written the tuple A, so it will update the write LB of this tuple. And finally, it will release the log. Okay, so that's for logging. For recovery, it's a lot simpler. We just use the following data structures. So for, again, LSN vectors, we maintain a recovered LSN vector. We call it ROV. This indicates for each log, the position of transactions we have already recovered. And we also have ending LSN vector. This is exactly the log file sizes. So besides this LSN vectors, we also maintain transaction pool per log. And we also maintain the max LSN per log. So basically this indicates the max log sequence number of the transactions we have read from the log. So the flow of the recovery basically look like this. So we have the recovery manager per log and a bunch of recovery workers per manager. So the recovery manager will decode transactions from the file and push it into the transaction pool. And also it will update the max LSN. And on the other side, the recovery worker will automatically EQ a transaction T such that the T.lv is no larger than ROV, and it will replay T. And after that, it will automatically update the corresponding dimension of ROV. So for the evaluation, we have carried out a very comprehensive evaluation of Taurus. So we run it on NVMe drives and hard drives, and also RAM disks. And then we also tested against different benchmarks, including the YCSB benchmark and TBCC benchmark. So due to the time limit here, we just want to discuss the YCSB benchmark performance on NVMe drive. So the figure in the bottom left is about logging performance. So the y-axis is the throughput in million transactions per second, and the x-axis is the number of worker threads. So we can see that the no logging baseline performs the best. We see that's the performance upper bound, and the sequential data logging performs the worst. Basically, that's bounded by the bandwidth of the single disk. We can see that the Taurus command logging scales pretty well, almost linearly. The figure in the bottom right is about recovery performance. So we can see that the Plover actually performs quite well in recovery. So this is because the Plover writes multiple log records to many log files, so that each log file contains all the information it needs. So it does not have to resolve any dependencies during recovery. So each log file can just recover on its own. So that's why it's very fast. But we can see that Taurus command, although it has to resolve dependencies, but with more worker threads, it can catch up with Plover. So overall, Taurus command logging can outperform Plover by 2.6 times and serial logging by 15.6 times. In recovery, Taurus command can outperform serial baselines by up to 42.6 times. Thank you for listening. I will be on the job market in the year 2022. So if you have any job opportunity, please contact me.